I am absolutely thrilled you're here today. We're going to take an action you've probably done, or at least seen 1,000 times, and we're going to completely pull back the curtain. Our goal for this explainer? Revealing the hidden physics driving it all. We're talking about the raw mechanics of motion. Specifically, we're going to explore those invisible pushes, pulls, and turning wheels that dictate exactly how energy transforms and moves through our physical world.
To truly understand these mechanics, I want you to picture something vividly for me. Imagine the immense, almost overwhelming physical strain of a bicycle race. You're at the very bottom of a massive, daunting incline. Every single fiber of your being is telling you, wow, this is gonna hurt. But what's actually happening beneath your feet in that exact moment? Well, today, we're gonna make those invisible forces completely visible.
Okay, let's dive into this. We're on the hill, your muscles are absolutely burning, the pedals are churning, and the tires are desperately gripping the asphalt just to keep you from rolling backwards. It feels like an uphill battle because, well, it literally is. But in the world of physics, this intense struggle isn't just about pain or endurance. It's this beautifully precise interaction of specific variables. To really understand this grueling climb, we need to break down the actual mechanics of what you're doing to that machine. Let's look at the very first core variable. You know, that burning strain the rider feels in their legs? Actually, scratch that. It's more like an agonizing fire. In mechanical physics, we just define that as effort. Simply put, effort is the push, the pull, or the twisting action required to do actual work in a system. When you're fighting gravity on that steep incline, the literal physical push you apply against the rigid resistance of the hill, that raw, demanding force, that is your effort. It's the absolutely crucial input required to make anything happen. So the crucial point is how that effort actually transfers to the bicycle itself. You aren't just pushing the bike forward with your hands, right? You're pushing down with your feet in a circle. If we zoom in on that bike pedal, we see a very specific type of effort, that downward stomp that creates a twisting force to turn the crank. That's called torque. Torque is just rotational effort. It's the muscular force you generate strictly applied in a circular motion. Now, all that intense physical effort and torque has to result in something, doesn't it? Otherwise, you're just standing still on a hill, sweating for no reason. And that brings us to our second core variable, flow. If effort is the hard push, flow is the direct payoff. It represents the speed or the rate of motion that comes from the effort you just applied. You push the pedals hard, and the bike moves. That forward movement, the literal linear velocity of the bicycle traveling up the hill, is your flow. But just like effort has a rotational cousin called torque, flow has a rotational equivalent too. In physics, we call it angular velocity. Think back to our bike analogy for a second. As your body and the bike travel forward, the pedals and the wheels are spinning in rapid circles right beneath you. How fast those pedals and wheels are turning, that is your angular velocity. It's simply the rotational flow that results directly from your rotational effort. Now, what's really interesting here is how cleanly all these physical concepts divide into two distinct camps. It's like a giant puzzle falling into place. We have our two columns. On one side, we have effort, which covers both straightforward force and rotational torque. On the other side, we have flow, which captures both linear velocity and angular velocity. Mentally distinguishing the physical push from the resulting speed gives us this perfect, crystal clear map of mechanical motion. And here is where the source material gets truly fascinating. All that burning effort from the rider doesn't just vanish into thin air. Energy literally never does. It transforms, and it travels through a system. During our grueling hill climb, the energy you put in has to navigate a very specific mechanical pathway through the bicycle's components to ultimately give you that forward flow. And this brilliantly illustrates exactly how that journey happens. It all starts as chemical energy, the biological fuel and calories burning right there in the rider's legs. The legs pump, converting that chemical power into mechanical rotation at the pedals using torque. Finally, the bike's chain transfers that rotation to the wheels, which grip the road and convert it into mechanical translation, or forward movement. It's a precise map of work, moving from a biological burn straight into kinetic motion. It's pretty amazing when you think about it. But let's get back to our rider for a second. The legs are screaming, the torque is totally maxed out, the flow is agonizingly slow. And then the climax of the climb. You reach the absolute peak of the hill. The intense, grueling uphill struggle is suddenly over. The terrain levels out, the horizon drops away, and instantly the mechanics of the entire situation completely shift. The agonizing resistance disappears, replaced by the incredible, rushing relief of the descent. Which brings us to a fantastic interactive riddle from our source material, posed by a conceptual character named Commander Energy. Commander Energy asks, if you are coasting down a hill very fast without pushing, do you have high effort or high flow? Think about the two columns of variables we just mapped out. What exactly happens when that steep incline reverses into a steep drop? Take a second to actively apply what you've just learned to this brand new scenario. Aha! The answer is high flow and essentially zero effort. Think about it. You are absolutely flying down that hill. Your linear velocity, your flow, is massive. The wind is roaring in your ears, the wheels are spinning with incredible angular velocity. But your feet? They are perfectly still. You aren't pushing the pedals at all. There's no force and no torque. The pushing force is practically gone. So, what does this all mean? The deeper meaning behind Commander Energy's coasting challenge is incredibly profound for understanding physics. It proves that these variables, effort and flow, are definitely not static numbers. They're part of a highly dynamic, constantly shifting relationship. Physical movement is a constant negotiation between the two. The descent shows us that, thanks to gravity and momentum, you can have massive speed, huge flow without needing a constant, continuous new input of effort from the rider. So, to summarize the overarching concepts we've explored today, we have this wonderfully elegant conceptual framework. Effort always equals force and torque. Flow always equals linear and angular velocity. And energy constantly transforms through these precise variables to create and sustain motion. Why does this mapping matter to us? Because it literally gives you the ultimate decoder ring for understanding how work moves through any mechanical system in the universe, not just a racing bicycle. Let's see how this builds into your everyday life. We've mapped out the pushes, the pulls, and the wheels. But you don't need a bicycle to experience these physics. Next time you climb a steep set of stairs, I want you to ask yourself, where is your effort going? What kind of force are you actively applying against gravity? And ultimately, what kind of flow are you creating with your own body? Keep looking for these invisible mechanics because I promise you, they are everywhere around you. Thanks for joining me for this explainer, and stay curious.